Hey there, welcome back to the Flex Diet Podcast. I'm your host, Dr. Mike T. Nelson. Today on the podcast, we've got a super special interview with Dr. Keith Barr. We're talking all about testosterone, cortisol, and the role of collagen protein. As always, this podcast is brought to you by the Flex Diet certification. So if you're listening to this right after this podcast came out, the Flex Diet certification is now open for enrollment. It'll be open from now, when you're listening to this, through June 13th, 2022 at midnight. So go to flexdiet.com, flexdiet.com, for all of the details and the information. If you're listening to this outside of that time, you can still go to flexdiet.com and you'll be able to put your name on the waiting list. So the next time that it opens, you will be notified and you'll get lots of great information for free delivered right to the old inbox there. So go to flexdiet.com for all of the information. And speaking of the flexdiet.com, we've got lots of great expert interviews there in the certification from the likes of Dr. Stu Phillips, Dr. Jose Antonio, Dr. Eric Helms, Dr. Dan Party, Dr. Hunter, and many, many more. So I tried to include lots of expert interviews in addition to all of the coursework there, which is over 20 hours. So that if you want to take a deep dive and talk to actual researchers and practitioners on different topics within that, that's all included there also. So coming up next here is an interview with Dr. Keith Barr. This is one I've been working on to do, honestly, for several years. I read his research and been following it for quite some time, and it turned out great. It is very technical at times, so you may have to listen to it a couple times. Or if you have any questions, drop me a note. I did try to include as many of the references here as I could, but I was not able to get all of them. And we talked about everything from the effects of testosterone. This is if you're in a normal level versus a supraphysiologic level. And you may be surprised by what he says about the effects of testosterone for building muscle in a normal range. And the surprise is probably not really needed, which is pretty crazy. We talked about the effects of cortisol. And in research, what you find is those who have the highest levels of cortisol are actually able to add more muscle, even though cortisol is considered a catabolic hormone. We talked about nutritional strategies you can do to manage that. Differences between men versus women, especially related to cortisol, how this impacts intermittent fasting and other periods of stress. And then we talked a lot about collagen. So collagen has been, and I've written about this in academic textbooks and papers before, that it was pretty useless. And this was looking only at sort of a muscle-centric approach. So it is true that collagen doesn't really stimulate muscle protein synthesis at all. But Dr. Barr and others, Dr. Shaw, have done some really interesting research showing that it may be beneficial for soft tissue. So if you have some soft tissue injuries you're recovering from, or you just want to reduce your risk of them, this is something that I've been using with my one-on-one clients for almost like 3 years now. So again, I don't publicize everything that I do with one-on-one clients, but I think enough time has passed with this that I wanted to share all this information with everyone, and I wanted to get it directly from the source who's done a lot of this research. So we'll learn how do you use collagen specifically for soft tissue. Should you change your training? Should you do different types of training? Now, this can be especially beneficial for recovery from some kind of niggly injuries. This is something that, again, that I've used with one-on-one clients for quite some time. And again, anecdotally, I found that it works really, really well. So Dr. Keith Barr talks all about that and a bunch more. So sit back and grab your favorite beverage and enjoy this wide-ranging talk from Dr. Keith Barr. Hey, welcome back to the Flex Diet Podcast, and I'm here today with Dr. Keith Barr. Thank you so much for taking time on the podcast today. We really appreciate it.
Absolutely. Pleasure to be here.
Yeah. Today we're going to get into all things collagen, a little bit more related to maybe injury recovery and performance. But for people who may not have heard of you, do you want to give yourself just a little background about how you got into research? And I know you do also very much applied stuff too. So I'm always fascinated by that, of people are running research and then also applying it in the, shall we say, the real world at the same time.
Yeah. So what I did is I started in the applied field where I was a undergrad at the University of Michigan. I became an assistant strength and conditioning coach. So I started as in that kind of applied vein, and then I went on to do a master's at Berkeley, a PhD at the University of Illinois, and then a postdoc at Washington University. And along the way, I was really focused on how exercise, nutrition, age, and disease alter the adaptation of musculoskeletal tissues. So how do we improve and optimize performance using exercise, nutrition, and maybe hormonal interventions throughout the lifespan? So how does it change? How does our response change as we get older? All of those types of ideas, and some of the best things that we can do are manipulate the loads that we use as well as the nutrients that we supply our body with.
Great. And I know you did some early work on testosterone also, if you wanted to touch on that, because I think its role a lot of times is misunderstood, and there's a huge difference between, are you hypogonadal, so you're real low, are you kind of in the middle, what we'll say, quote, natural area, and then if you use, other special supplements to get to a supra physiologic level. Because I think humans, we tend to think that everything is linear, but it's very much a non-linear dynamic.
Yeah, so we had shown some of the work that Eric Davidian had done in mine and Sue Bodine's labs, where he was manipulating testosterone both in male and female animals. When he did it in male animals, basically what he could do is he could castrate them at different ages, and without testosterone had no effect once you reach maturation. The only time they really had an effect is when they were during growth, so at their puberty, so they were still growing through puberty. Same thing is really true for the females when you were supplementing with testosterone. So when we add external testosterone, you need a secondary stimulus. You need either resistance exercise or you need pubescent growth in order to see an effect of testosterone. So for most individuals who are adult, so they're fully mature, skeletally mature, we're not seeing a huge effect on muscle mass until you're really super physiological, the kind of thing that you only get when you're supplementing quite extensively as a performance-enhancing drug user. When you're in physiological ranges, it doesn't really have that much of an effect, largely because most of the steroid effects are seen around 5% occupancy of the receptors. So most people who are not hypogonadal, or they're going to be able to reach that level as men without really having to supplement, without really having to worry about it as you get older. That didn't seem to have a really positive effect. And the thing we always see with testosterone is it decreases breakdown in muscle. And that's its primary thing that's happening in muscle. And that's just making your muscle quality go down. You might have more muscle, but that muscle doesn't have as good quality because that turnover rate, how quickly we can kind of get new proteins in to replace the old proteins. If we slow that down, all we're doing is accumulating damage. So we accumulate oxidative damage, lipolytic damage, all kinds of different things that happen to your proteins post-translationally that can have a negative effect on how that protein performs. So if we decrease protein degradation, in the short term, yeah, we might have a beneficial effect, but in the long term, it's going to have a negative effect. And we see that because men's muscle quality isn't as high as women's when we take it down to the per cross-sectional area
Hmm. So if we throw rules and ethics aside for right now, and you're getting close to, let's say, the high end of a weight class sport where speed and power are primary eminent, would using anabolics, at least testosterone, we'll keep it to that, could that be a negative at that point because you may be adding weight that doesn't function quite as
It's
well per
not.
se?
So in a situation like that, the benefits are actually not happening really from your muscle. They're happening from the central changes. So
Mm.
the aggressiveness that's happening. So when you're going to do strength, speed, or power, if you're hyper aggressive because your brain is easier depolarized, which we know that happens with testosterone, so you can activate things really, really quickly. That's going to potentially have a beneficial effect. The other thing that we see in our connective tissue work is when we add testosterone, it makes the connective tissue stiffer. And that's really where we think a lot of the performance benefits are happening, those two components. The brain is going to allow you to make a decision quicker and to do a movement faster. And the stiffness of your connective tissue is going to go up. And so those two things together are going to increase your rate of force development.
Ah, very cool. And I like the part you said about if you're in the normal range, going from say 450 to 850, you're not going to see a huge difference, which I think is probably kind of surprising to most people. I mean, I would agree, and most of the literature supports it, even though we don't have a ton of data on that in humans. I think Bazin did some stuff in the 90s where they chemically castrated some males and then tried to supplement them back in a couple different areas.
But there's good data from prostate cancer patients where if you
mm,
use drugs to block testosterone completely, they are still able to grow their muscles just the same as people who don't have that negative effect on their testosterone. So you could be at zero testosterone or very low testosterone as a man, you can still gain muscle mass from the resistance exercise, and the rate at which you gain that mass is the same as somebody who hasn't been altered by those drugs. So that's that from the prostate cancer literature. When people are going through chemotherapy that are designed because that the prostate is so androgen intensive, so it's so dependent on the androgens for growth that it's commonly used to drop testosterone as low as possible. You can still gain muscle mass in that situation. And so there's good data there. There's good data in the rate at which women add muscle mass and strength that suggests
yeah, that
that
was my next
testosterone isn't
question.
really going to do that much.
Because I think in mature males and females, the rate of gaining muscle is similar if you control for other factors, even though they have much, much less testosterone than males.
Yeah, and there's good work from Keratin where he showed that their strength, that women's strength will increase faster or greater than males.
Hmm.
The baseline is lower, but they respond to resistance exercise as well, if not slightly better than men.
And are they responding better because they're at a little bit lower of a baseline, or is there some other factors there maybe?
They're at a little bit lower of a baseline, but they're also, and so that's probably sociological. That we don't encourage women as much as men to perform strength exercise, so they're not necessarily starting with as much muscle mass. But then Shriner has shown that women have a higher protein synthetic rate, and like I said, the testosterone lowers breakdown, so that women have a higher breakdown rate as well. So the turnover rate in a woman's muscle is actually higher than a man's. But one of the things that testosterone is doing is it's binding to the glucocorticoid receptor and inhibiting cortisol, some of the cortisol effects. So one of the things we see is under stress or under high levels of glucocorticoids, so these steroid hormones that are supposed to drop muscle mass, far more effective in women at dropping muscle mass than men, because without the protective effect of testosterone, the glucocorticoids, the cortisol in the system is going to drop muscle mass much faster. And Subodhine and Dave Furlow here at Davis showed that really nicely in animal models, where when you add, any of these glucocorticoids to males and females, the females drop muscle mass much faster than the males.
So would a kind of an extrapolation of that be that females may be more sensitive to the effects of overall stress in related to muscle mass, or is that a little too much of a leap?
Insofar as that cortisol will go up with stress. The bigger issue for your listeners, if they're looking at metabolic flexibility, I'm sure that a lot of them are doing things like time restricted feeding or some fasting. That means, what it means to us is that the cortisol levels in a woman are going to go up the same as they are in a man. They're going to reach their highest right before breakfast, right before whenever you break your fast. And it means that the women's muscle are more prone to losing muscle mass from fasting than men are. And so they're not necessarily going to see this as much of a beneficial effect as a male would from doing some of the time restricted feeding or intermittent fasting that a lot of your male listeners will have tried at least.
Oh, that's super interesting, because I have had some females do shorter fasts, but only maybe once a week, once every other week. And I can't think of a single circumstance where I've had females do longer fasts, like a 16-8 or those types of approaches, where I've had some guys have some pretty good success with that. I would say in general, at least anecdotally, males tend to do better with longer fasting. And I've always wondered if that was something more physiologic, which sounds like it could be, or other factors.
It's definitely physiologic. You can see it from the cortisol effects, but you also see other hormones that are really important in protein fasting as well, like FGF21. So I have a colleague, Karen Ryan, and she injects FGF21 into the brains of males and females, and then she gives them access to the individual macronutrients. So she puts a plate of protein, fat, or carbohydrate out. And when you inject FGF21 into the brains of males, they will go and almost exclusively eat protein. And the females won't do the same thing. So we actually have very different drivers for both our adaptive response, so our metabolic response to a fast, but also in our cravings that result from the fast. So whereas males might crave a little bit more protein-rich food, females don't have a specific, as much of a specific crave in that way. And that could also play a role in how much muscle mass is maintained in these longer or intermittent type fasting.
Oh, that's very cool, because again, anecdotally, I'll ask clients, like, when you get super stressed, like, what foods do you crave? And guys typically will be, some foods, but it's not uncommon to hear, I just want like a big steak, right? Where rarely do I ever hear females say that. I've always wondered if there's something physiologically or if it's just more a societal convention. So it sounds like there may be something to that physiologically.
Yeah, it's probably a little bit of both, but there is definitely a hormonal, a neurocognitive change that results from some of these hormones that are usually produced by things like the bile acid components that you get FGF21 from. And so because there are these kind of cues that we're getting from the physiological response to either feeding or fasting, there are going to be sex differences that are going to have significant effects on our muscle mass, and as a result on our basal metabolic rate and other things.
Awesome. And if someone wanted to, let's say, gain muscle or lean body mass, I know I'm kind of using them interchangeably, at the fastest rate without any exogenous drugs, is there some types of strategies they should do around cortisol or other methods?
Yeah, absolutely. So the interesting thing is that the cortisol is probably the best predictor. So the higher the cortisol, the better you are going to be at gaining mass. It's basically,
that seems like the inverse of what most people would guess.
Right. It is the inverse of what people would guess, and probably the best reason, the best rationale as to why is that what you've done is you've done the hardest exercise. So that's the greatest stress. And so what we know is if we want to build our muscle mass, what we're going to do is we're going to lift any weight to failure. So you don't have to lift a huge weight. You can lift a relatively light weight for yourself, but as long as you keep going until you can't lift it anymore. And the key there is that you don't rest at any point. You just keep pushing, because what we know is that, and what Stu Phillips has shown quite nicely, is that what happens when we get a muscle to failure is that's the only time in humans where we recruit all of the fibers within the muscle. So all of the fibers within the muscle get that molecular signal that's going to tell the muscle it's going to now want to get bigger. And so if we don't go to failure, we're only getting part of the signal. So many of the fibers don't actually get the signal to grow. But at failure, we're recruiting all of the muscles. We're giving a signal to all of the muscle fibers within the muscle we're working. And that's why we use any weight to failure. So it doesn't matter light or heavy. You can get bigger by using anything and lifting it to failure, and then supporting it with a good high quality proteins that are complete proteins. So whey is the gold standard because it's easily digestible. But anything that's going to be a leucine rich protein that's going to have all of the nutrients. It can be plant-based, it could be animal-based. It's not a huge difference. But what you're looking to do is you're looking to support that strength training with that protein dose. And those two things together, we know the molecular mechanism. So what we had shown very early on during my PhD is that how big your muscle is directly proportional to the short-term activation of a protein kinase called mTOR complex 1. And that one's also activated by amino acids. And they activate mTOR complex 1 in different ways. And so what we know is that the two things together are additive. So when I do my lift and I get that signal, at failure, I get that signal of tension across that muscle fiber. That muscle fiber is going to change that tension into a chemical signal that's going to turn on mTOR complex 1. And the way that it does that is different than the way that amino acids are going to do it. And so the result is when we do them together, we get a further increase greater than we would get with either feeding alone or with strength training alone. And so combining those things together is going to give us our biggest growth response.
Very cool. And I think some of the stuff from Nick Bird's lab, or Nick Bird when he was working in Stu Phillips' lab, showed, as light as 30% of 1RM, which it's much lighter than I think most people would realize, but they did that with leg extensions. Again, Yep. That exercise was taken to, momentary failure, or you couldn't move the weight, or whatever definition we're using for failure in this context.
Yeah, they go to positive failure. And when you get to positive failure, you got that beneficial effect. The biggest effect, whether it was 30% or 90% of 1 rep max. And then they did the follow-up study looking at 30% or 80%. They trained them and they found that the increase in muscle mass was the same between them over, I think it was an 8 or 12-week training period. But what they found was that the increase in strength was greater for the 80% groups. So they had a couple of 80%. So when you're lifting at 80% of your 1 rep max, you got a bigger increase in strength, but the muscle mass was the same.
Yeah, and I saw Stu here a couple of weeks ago. He said to say hi, by the way.
Very good.
And he was saying there's some even newer studies where they then took the group that did, say, a low, like 30% of 1RM, and then gave them a couple practice sessions on what they were going to test them on. And then he said that the strength difference between those two groups got to be even less than. So there's even some debate about if you use some other method and maybe you can add some muscle that way, how long would you need to train that quote new muscle to impart strength changes to it then too?
So the neurological adaptations are going to be very, very quick. They're the fastest adaptations that we have within the strength paradigm. But once you make those neurological adaptations, you're also going to have other structural changes that are going to be important for how well you transmit the force. And so, yeah, so what we say is that if you want to get stronger, you lift a heavy weight. If you want to get bigger, you lift any weight and you go to failure.
At some point, can you make up for not going to failure by just doing enough physical volume to compensate for that? If you have more time and let's say your goal is kind of more strength and hypertrophy at the same time?
Yeah, so you can go, the volume component is important for size. It's not important for strength. So it doesn't look like we need to do a lot of volume if we want to increase strength. But if you want to increase size, you can do less weight and do a lot more volume. And a lot of people in the field know this because a lot of bodybuilders, that's exactly what they do. They love to be in the gym. That's their job. They in between sets, they talk to every single person in the gym. They're going to spend 5-6 hours in the gym. Frequency, intensity, and duration is what we manipulate. So if you want to have your duration be super long, you just do it with a lower intensity. And so that's basically still right within that overload principle that's really the key to growing muscle bigger and stronger.
On the catabolic side, is there anything we should look at nutritionally to maybe mitigate that? I know there's always a bunch of talk about carbohydrates immediately after training. And then I think it was Stu's lab again showed in terms of insulin release, if you're just having 20 to 40 grams of whey protein, you have enough insulin release to kind of stop the catabolic process. So maybe from that side, it's not as important as we thought. Obviously, you'd be replenishing glycogen if you're going to do a session within a short period of time right after, which would be a different circumstance.
So the classic study there was by Kevin Tipton. Stu was on that paper as well, where they fed either all amino acids or essential amino acids. And when they just fed enough of the essential amino acids, they got a decrease in degradation. Because a lot of times what we're looking at for degradation isn't something where we're driving degradation or we're inhibiting degradation through the insulin stimulation, because insulin stimulation for the first 6 hours after exercise is inhibited. And so after resistance exercise. And so what we're actually getting as far as the degradation is used to drive synthesis after strength training. Because what we're looking for is essential amino acids. If we don't have a source from the diet, because somebody's doing it fasted, we have to break down protein in order to free up amino acids, specifically the essential amino acids. And so what Kev Tipton's 1999 paper showed that is that if you bring up the essential amino acids, you drop protein degradation. And that doesn't necessarily need any insulin response. There is some arginine in that essential group that he gave to give maybe a little bit of insulin. But the insulin component, because when we do heavy exercise or we do strength exercise, we get that load across the muscle. Troy Hornberger has shown that when you do that, you activate a different system that's parallel to the insulin system, and that's activating mTOR in a way that doesn't need insulin or IGF-1. And then what you get is you get feedback inhibition. And so my former PhD student, Lee Hamilton, had shown that after exercise, the association of either IRS1 or IRS2, these two insulin signaling substrates, goes down. The association with the insulin receptor goes down. And with the PI3 kinase, they go down. So what you're doing is, and Rennie Koopman showed a long time ago now that what happens after lifting heavy weights is you get a period of insulin resistance that lasts maybe 3 to 6 hours while you're getting this feedback inhibition on insulin signaling, because you don't need it, because you're able to activate these systems independent of insulin. And then 24 hours later, you actually have an increase in insulin sensitivity, because this whole system is kind of reset insulin signaling to some degree. And so it allows you to then to get a bigger stimulus from the same amount of insulin. And so we think that that's one of the really important things that resistance exercise does, is it resets a lot of the signaling cascades that are downstream of insulin or downstream of some of the metabolic flexibility things that we look at. Because we just had a paper come out where we did 4 bouts of exercise over 2 weeks. And then 72 hours after the last bout of exercise, we looked at protein turnover, and we looked at signaling through mTOR, and mTOR signaling is significantly lower in the muscle that you've exercised 4 times over those 2 weeks, but your protein synthetic rate is higher. So what we're doing is we're dropping a lot of the baseline level of mTOR activity is going down. The baseline level of certain aspects of insulin signaling are coming down. But then what we're doing is we're returning the ability to signal at the next meal or at the next bout of exercise. And so what we're doing is increasing what we call the dynamic range of the system. What we do is we have it go we activate the system really at a high level. And then for 2 or 3 days, it's going to actually go down below baseline. And then we're going to be able to activate it again. And every time we have a meal, because we've got this greater dynamic range, we take more of the protein that we eat, we make it into muscle in that space. And Stu again has shown that 24 hours after your last resistance exercise bout, you're still better at building muscle than if you didn't do the exercise bout yesterday. And so a lot of that is because what we're doing is we're we're modifying the dynamic range. We're dropping the baseline of things like mTOR activity and insulin signal. And then when we get it, that signal comes back because we eat, we get insulin. Now we're going to have an insulin signal. Now we've got this much greater range. We go from a lower starting point to the same level of stimulation. That change is much bigger, and that means we get a bigger biological effect from the same signal.
And so the main insulin effects you're talking about are related to the non-insulin mediated uptake category, I guess you could say. Is that correct?
So there's a lot of the non-insulin mediated stuff. So yes, so we know that the insulin signal for glucose uptake can be basically replaced by a contraction-based signal. We know that a lot of what insulin does is change blood flow, get blood flow to go to the tissues where we're supposed to store amino acids and sugars, and that's to our muscles and certain fat depots. When we do exercise, we don't need the insulin to change blood flow. Now that exercise has changed blood flow by producing metabolic byproducts, so we have greater blood flow, so we don't need as much of the insulin effect to get more of the substrate into the tissue that we want it to go to.
Very cool. And the new study you were talking about where I think they did heavy stimulation for a shorter period of time. If you were to translate that into humans, and assuming that's the same, would that be an argument for doing maybe less frequent but more intense bouts of exercise then to try to raise that ceiling effect? Or what would that look like if you could translate it into humans?
In what group?
In probably like intermediate level athletes. So not beginners, but people who have been, training for a while, but not elite level athletes.
Yeah. So yes, I think that people get into the same routine of their exercise training. And so we adapt to that. And so it's less and less of a stimulus each time. And there's a Japanese group that shows if you do the same exercise over time, and our new paper as well showed that even the second bout of resistance exercise, where we saw mTOR activity go up 20-fold after the first one, 6 hours after the second one, it goes up 5-fold, or three to 5-fold. So we're not seeing that huge response that we saw. And the Japanese group showed that over time, that those individual responses to the exercise are coming down. But if you take a 2-week break and you do the exercise again, bang, there goes that molecular signal comes back. So there's two ways you can do it. You can take a little time off and then come back and hit it with the same type of exercise. You'll get a bigger stimulus from that. Or what's more kind of what needs to happen more for people who just go out and train the same way every day is you just have to throw in, say, 20% of your sessions or 20% of the time that you're going to be exercising at a much higher intensity. So adding those high intensity intervals is going to have a huge effect. And we know that from work from the Buck Institute. Simon Melov had shown that when you lift weights or when you do high intensity interval training, that the transcriptomics, so all of the messenger RNAs within your muscles, if you're older, they look like you're younger again. Because that high intensity exercise, that's getting outside of the comfort zone. That's giving you a greater stimulus to see things like muscle growth response genes, insulin signaling genes, mitochondrial genes. They have a much bigger effect, especially in an older population, if you do high intensity interval training. And so yes, I do think that manipulating that intensity is a really important thing to do for all levels of athletes, and even athletes who are just training for life. So they're not going to train for any competition. They just want to feel like they're still making progress. They're still making the changes towards their goals. Those are the goals could simply be healthy body and low body fat or whatever it is. All of those things, the idea of going high intensity, throwing in 10 to 20% of the work that you do as high intensity work is absolutely essential.
Yeah, that matches a lot of Martin Gabalia's work. He's done some stuff on that for several decades. And so for practical area, would you look at like 20 to 30, 40 seconds, like a Wingate type protocol where you're going as hard as you can, more on the complete rest, and then try to keep that quality of work high again when you do the second interval?
So you can do it. There's any number of ways you can do it. What you're looking to do, there's three areas that we're adapting really well to endurance exercise. One is our long, slow endurance exercise. And the other two windows are our sprint intervals and our high intensity intervals. Sprint interval is between 6 seconds and 30 seconds. You do those 6 to 30 second intervals, you're using ATP faster than you can produce it because you're going from stored phosphagens to glycolysis. So you're at that transition point between two metabolic systems. It's like if you were driving your manual transmission car and you're accelerating, you have to pause for a second while you put in the clutch and you shift. That's what your body is doing to some degree. So at those transition points, you're using ATP faster than you can produce it, and that's going to give our body a signal. The second transition point is between glycolytic and metabolism and oxidative metabolism. That's happening about 1 to 3 minutes. So we're looking at those intervals at like 30-second intervals, 2-minute intervals. Those are great intervals to do. And those are the intervals that are going to give us those metabolic signals, those things like ATP. So ATP consumption, ADP is going up. ADP activates the AMP activated protein kinase, and we get a really important signal from that. When we go long for a long time and we go at a relatively low intensity, that long, slow distance, we get a different signal that's driving the adaptation that we're making, and that's a calcium-based signal. And so that signal is likely CAM kinase based. So now we have two different signals. One's an intensity signal, one's a duration signal. We tend to be really good about the duration signal, especially if we're cyclists or swimmers, or we can get in there and go for a long time. Getting that intensity signal is something that we're less proficient at because it's more painful. It hurts to do, and fun. So it is not the fun one. It's the one that makes you feel like you're going to vomit at the end. And so people shy away from that one. So when we're trying to do this, we're trying to mix these two signals in. And we mix these two signals in such a way as we can maximize the adaptation and minimize the mechanical impact. Because especially if we're running, if we're going to do a lot of high intensity running, the impact force is going to be much higher. So our mechanical load is going to be much higher. The likelihood of us getting an injury is going to be much higher. And so that's not necessarily where we want to do it. We want to do it when we're rowing or cycling or swimming, where we're not having as much of an impact force. You can do it with the running, but now your overall percentage of high intensity work has to be lower if you're a runner than if you're a rower, a swimmer, or a cyclist.
Yeah, I'm a big fan of the rower because a lot of my online clients, they're not training to be sprinters, and I don't know how much I trust them to run full out at 90%. Yeah. And even if absolutely. They could, the impact over time, it's like you're looking at the cost to benefit ratio. If you're going to be a sprinter, then yeah, of course it's specific. But if you're not going to be a sprinter, I think you can use other modalities and still get that high intensity point without the mechanical trauma also.
Yep. No, exactly.
And probably a good time to shift gears towards collagen. How did you get interested in collagen research?
Yeah, so we for years and years we've been engineering musculoskeletal tissues. So I started doing this with Bob Dennis at the University of Michigan, where we would make little muscles in a dish. And Bob is this crazy engineer guy who's smarter than anybody else in the world that I know. And he had come up with this idea that when you do deep space flights, you're going to need a motor, and that motor needs to be able to repair itself. So what would be perfect is if you had a muscle that could produce all of the movements that you were going to need in order to have like some 10-year long flight. And if something went wrong with the motor where it didn't work, it would actually repair itself. And so his idea was if we could engineer these muscles, we'd have these motors that could be tuned to do different things within, a body or a spaceship or whatever. And so he's got great videos you can still find online where he's got little fish that are floating and he's got two little engineered muscles on either side of it. And he then could contract them alternatively and cause the fish to swim around. Huh. So I went and worked with him for a postdoc, and I was engineering muscles. But when we put those muscles onto those little fish or onto any other kind of machine, they would always fail at the interface where we just tie them on. So they would always pull out, or they would always have failures there. And we realized that what we didn't have is we didn't have a working tendon. And so what a tendon does, and so with Ellen Aruda there at Michigan, what we showed was that tendon is a variable mechanical tissue. So we were doing these things where at the muscle end of the tendon, it's very stretchy. The bone end, it's very stiff. And that allows me to attach that stretchy muscle to a stiff structure. And so we started to think about, oh, well, we engineer all these muscles, we should engineer some tendons and ligaments. And so we started doing that. And then I moved my laboratory, my first lab, to Scotland, and I had a PhD student there named Jennifer Paxton. And what we were doing was engineering, we were trying to engineer these ligaments, these tendons. And we said, well, if we're going to have a bone, a tendon, and then a muscle, that's three tissues. It's really hard to do. So let's just start by making a bone, a tendon, and a bone. And that's a ligament, bone to bone. And so she started engineering ligaments. And what we found really early on is that if we wanted to make a strong ligament, we had to add proline, and we had to add some of these other essential amino acids that aren't necessarily found as high a level as we needed. And so when we added proline into the mix, we got a big increase in the strength and the stiffness of our ligaments. And so I did some simple searches around to see what are proline-rich foods, and gelatin came up as a proline-rich food. It's just collagen itself, where the collagen has been boiled to produce the gelatin, and so it still forms a gel, and it's really good that way. And so what we had figured is that, well, if this works in our little engineered ligaments, that when you give proline or you give glycine at high levels, there's a group from Brazil who just gave lots and lots of glycine, and they saw that the tendons and ligaments got better. So we figured that this might be a way to do it just by giving dietary collagen. And so we started by doing that. We would feed people collagen or gelatin. We could take their blood and put it onto our engineered ligaments. And before you had the collagen and the vitamin C, so you're overnight fasted, that blood made a ligament that's really weak. But the ones that you got an hour after eating the collagen or the gelatin, that made a much stronger and much more collagen-rich tissue. So that was telling us that maybe there's something interesting there. And then we did a study together with Greg Shaw at the Australian Institute of Sport, where we fed people for 3 days. We fed them either a placebo, 5 or 15 grams of gelatin. We had them jump rope 6 minutes, an hour after. And that's because we had, using our engineered ligaments, we'd shown that connective tissues adapt really well to short periods of activity. That if you do an hour's worth of exercise, your connective tissue is going to turn on, get maximal around 10 minutes, and then turn off even though you're continuing to exercise by 60 minutes, the cells aren't getting a signal that's positive. And so we were just doing those short periods of activity. And over the 72 hours, when we gave them 15 grams of gelatin, we could double the rate at which the bones within those subjects were producing collagen. And so that was telling us that there was, potentially something there. We hadn't done other proteins. We just did placebo control versus gelatin. The 5 grams didn't give us enough, but the 15 grams gave us a nice effect. And so we're actually starting a study right now where we're going to do pretty much exactly the same thing. We're going to compare our hydrolyzed collagen to whey protein, and to the third thing we have a vegetarian collagen made by a company out of the Bay Area here called Geltor. And what it is it's a recombinant collagen that's made in bacteria. And it's the only form of collagen in the world that's actually vegetarian.
So they'll just mimic the amino acid profile.
Yeah, it's got the same amino acid profile. So they build up and they use it already for cosmetics, where the collagen is used in cosmetics. And so now what they're looking to do is see whether that could be used as a supplement, and a dietary supplement in people. And so we'll have those 3 proteins compared to placebo control in a bunch of men and women, and we'll be able to see is it just any protein will work, so the whey protein is just as good as collagen, or is the collagen important? And is there something special about animal collagen, or can we just take in this recombinant protein, which has never been in an animal, and can we get the same thing from just having those amino acids in it? So I think it's going to be it's a super cool study. We're starting to recruit. So if your listeners are in the Bay Area, in the Davis area, and want to be part of it, they're more than welcome to reach out and join the clinical trial. We should have the clinical trial up on clinicaltrials.gov this month, so that we can, and our recruiting is starting. So
that's awesome. And it sounds like that may settle the debate between you and Stu about collagen versus whey.
Well, I don't have any debate with Stu, because I agree with him that it's not great for building muscle, because it doesn't have it's got almost no leucine. It's not a complete protein. The question that I have is whether there's something that the cells within connective tissue are getting from either the amino acids or some of the other kind of limited amino acids that you see in collagen that you don't see in any other protein. And those are the hydroxylated forms of amino acids. So hydroxyproline and hydroxylysine, some of our data would suggest that those kind of modified amino acids are actually giving a signal to cells, which could be important for the synthetic response that we see in response to dietary collagen.
Yeah, that was my next question. How much do you think of that is providing raw materials for building blocks, and then you've got the stimulus of exercise and potentially more blood flow to areas that don't get a ton of blood flow? And or is there some other downstream effects from the collagen that's signaling different things to go on, or combination of both?
Yeah, so the interesting thing that I told you is that when we take people's blood before and after they eat dietary collagen, and then we put it onto our engineered ligaments, the ligaments get stronger. And this is in a situation where we've actually got 5 times the physiological level of amino acids in the media already. So we're adding 10% of the volume is the serum, and we're getting more collagen synthesis. We're getting stronger ligaments, but we're not adding a lot of glycine or proline. And so what that's suggesting to us is that something else in the collagen is actually having the beneficial effect. And so we know that the vitamin C is important, but that's in all of the different groups. So the question then becomes, what is it, or is there something special about something that's within that dietary collagen that is driving this increase in collagen synthesis? And I think that that's the really important question that we're really keen to answer with this study that we've got going on now, because not only are we going to have whey protein, but we're going to have this collagen that doesn't have hydroxylated proteins in it.
Right.
And so if those hydroxylated proteins are important, we should see that collagen is better at stimulating collagen synthesis than whey protein. And it's also better than stimulating something that has the exact same amino acid profile, just doesn't have the hydroxylations. So it's going to be a super cool study in that way, because it has the potential to really pull out mechanistically what's going on.
Yeah, that's awesome. And so one thing I've done with clients based off of your research, especially with Dr. Shaw, was add 15 grams of collagen to their whey protein about 40 to 60 minutes before exercise with some vitamin C, thinking, maybe I'll hit 2 birds with 2 stones. I'll get the potential soft tissue effects per se, and then get some of the muscle effects per se. I assume you would generally agree with that in terms of practice.
So it depends on what we're trying to target. So if you're trying to target muscle, we're totally fine with adding it afterwards, because the reason that we put it in beforehand when we're looking at bone and tendon and ligaments is because they don't get the same kind of blood supply that the muscle does. So if we're looking to fix say, we have a hamstring pull. So somebody's pulled their hamstring, it's pulled off, or it's been surgically repaired or whatever, and we're repairing that tissue. Now what we want to get is we want to get both a muscle signal and a connective tissue signal. There's going to be blood flow after the exercise that we do, because that muscle is already pulling in blood flow. And so now we can do that as a supplement that we just do after, together with the protein, no problem. If we want to target it specifically to tendon, then what we're going to do is we're going to put it in beforehand. And you can do it together with whatever you want to do it together with. But yeah, we're going to try and get it in about 40 minutes to an hour beforehand, just so that when we're pulling on that tendon and we're squeezing all the liquid out of it, and then we're relaxing and we're squeezing and we're relaxing, we're getting that rhythmic movement through that tendon, we're going to get more fluid flow, and that more fluid flow is going to pull more nutrients into the proximity of the cells, and we're going to get more of whatever signal we're hoping to get there, using that kind of load as a way to target our nutrition to where we want it. So yeah, the way that you're doing it sounds fine. The way that we would kind of tweak it a little bit is if we're looking for a muscle signal, yeah, fine to give it afterwards. If we're looking for something that's more tendon or ligament based, we're going to give it, or cartilage based or bone based, we're maybe going to give it beforehand.
Got it. And would there be any downside to adding like 6 to 10 grams of essential amino acids with the collagen beforehand?
Not at all. Not at all. And it might be something where adding the whey protein together with the collagen is going to give us a better response. Sure. Because the whey protein are going to have all of the other amino acids that are necessary. The thing to remember is that collagen is a really simple protein. It's basically two amino acids. It's glycine and proline make up 2/3 of the amino acids within collagen. So the sequence goes glycine, any amino acids, and any amino acid, then proline. So most of what we see are glycine and proline. So that's one of the reasons why we are giving a dietary collagen, is because if we give whey protein, it's a dairy-based protein. It's a great protein. It's a complete protein. But what happens is after exercise, you'll see a drop in glycine within the body. And it's possible that we're getting a little bit of a limitation based on how much glycine is there, because it's not as glycine rich as some of the connective tissue. And there's some really nice work coming out of Luc Van Loon's lab that's showing that after resistance exercise, there's higher rates of protein turnover in the matrix than there is in the muscle. So the matrix has actually got more protein synthesis response to exercise than the muscle does. And we've seen that in a number of our studies, where when we give a stimulus for a muscle to grow bigger, we actually see collagen concentration go up, which means that the collagen is increasing at a faster rate than the muscle protein is increasing. And we've got a colleague in France who inhibits collagen synthesis when he does that. And what he shows is that you drop 50% of the strength gains are lost by inhibiting the increase in collagen synthesis. So we really think that the matrix is important. Whether it's sensitive to collagen as a dietary supplement, it's far too early to know. But we do know that the matrix is really important for the functionality of that muscle, the muscle's ability to transmit force and to become stronger.
I think it was Van Loon's lab that also had a study looking at different tissue turnover rates that they did from some surgeries, showing that basically the turnover rates were much faster than at least what I thought, because I had heard the old thing, which has kind of been sort of disproven now, that muscle will turn over in 90 days and soft tissue takes like 9 months, where all the newer data, and you're suggesting that might even be inverse, that some of the collagen processes may be turning over faster than muscle.
Yeah, so that study that Smeets was the first author on, basically what he had shown is that protein turnover in the ACL was actually twice that of the quadricep muscle.
Right.
And that the patellar tendon was almost the same as the ACL. And we know that it's load dependent because when he looked at the PCL, the posterior cruciate ligament, it had the same amount as muscle. So the loading, because the PCL isn't loaded a lot, the ACL is loaded quite a bit. That's where we're getting that dynamic difference between those two tissues. But yeah, it was quite illuminating to see that. We also have to understand that, yes, there is real good, very, very good data from Michael Kerr's group, from Katja Hennemeyer, using the bomb pulse that shows that, look, collagen turnover in the core of an Achilles tendon doesn't happen to a great degree. We might be, because again, that's using this radioactivity that you would find in the environment. It might be that we're able to recycle really well all of the protein and amino acids within the core. And so we don't see, say, a breakdown we don't see turnover overall, but we're able to recycle those amino acids, or it means that the core isn't changing and the outside of our tendons are changing quite a bit. And so we can't make any grand conclusion as to which one it is yet, but we do know that like metabolically, the outside of a tendon is far more metabolically dynamic than the inside. And so it's possible that we're seeing differences through the tendons from the core to the outside, and also as a function of things like exercise and nutrition and other components.
Yeah, that's fascinating. And then you also wonder about all the freak case studies you see of weird Achilles ruptures that, quote unquote, appear to happen out of, nowhere. And there's different, like Levaquin and different drugs seem to target Achilles heel injuries more often. And yeah.
So there's a whole bunch of things within that. One of the ACE inhibitors is got huge numbers of Achilles tendon ruptures with it. We know the fluoroquinolones have a huge number of Achilles tendon ruptures. So there are drugs that are specifically targeting things, and we don't know how they work. And it's still very early days to figuring out how they work. But yeah, there's definitely lots of really interesting things as far as how these tissues are turning over, what their turnover rate is, and how dynamic they are. Because there's really nice data in female soccer players that shows that the ACL gets bigger over the 8 months of a season. So as they train, the ACL got bigger, and then what you would assume is, since they were all college level athletes, is that in the 4 months that they took off, that tissue got smaller again. So again, these are highly dynamic tissues is what we're learning. And so what we're doing is we're learning how to support them with the proper loads. Like I just had Camille Herron in here, who's the world's greatest ultra marathoner, and she was telling she had gotten all kinds of bone injuries when she was a young runner. That made her go into science as a college student, and then she did a master's in bone biology and bone mechanotransduction. And she learned that the way that a bone worked is it had short periods of load, and you needed good amounts of rest, like 6 to 8 hours. And so the way that she trains is she trains twice a day, because she knows that by training twice a day, she gets 2 of the signals that last only a short period of time. Even when she runs for, say, an hour and a half or 2 hour run, she knows that her connective tissue only gets maybe a half hour of an adaptive signal from that 2 hour run. But if she was going to do a 4 hour run, which is not uncommon for an ultra marathoner, if she breaks that up into 2 hour runs that are separated by 8 hours, she gets 2 of the stimuli to her bones, tendons, cartilage to have a positive effect, whereas a different ultra marathoner who's doing that as a single session only gets 1. And so now what you get is you get these differences in how the body is going to respond based on how we're pairing up the exercise. I know that Brad Lindell had done some work where he had taken military recruits who get tons of stress fractures, and instead of having them run once a day, you had them run half as much twice a day, and stress fractures go down massively. So just figuring out how the different tissues respond to loading is really important for understanding what exercise training should look like based on what your injury history is, based on what your capabilities are.
Oh, that's awesome. And as we wrap up, I know you've talked a little bit about possible use of collagen and then certain types of isometric exercise. And I think that it's interesting, like high level sprinters, you talked about potential hamstring injuries. But if I think about the average gym goer, rarely do I ever hear of a muscle tear. It's almost always a soft tissue related injury. So is there something more for that population they should consider doing related to training?
Yeah, so again, that's one of the interesting things that happens, because as you train, basically you're training the stiffness of the structures that you're training based on how you train. So if I do a lot of fast training, my tendons are going to get stiffer. To do fast training, I can't do it against a lot of weight, so that means my muscle is not going to get a stimulus for strength, so I'm going to get a little bit weaker muscle over time. Now I have a stiff tendon and a weak muscle. That's when I get muscle pulls. Most people don't do a lot of their training fast. We've talked about that already. So that most of the average people aren't getting muscle pulls. What they're getting is they're getting tendon problems, and they're getting kind of these types of injuries where the muscle is stronger than the tendon, and now the basically when we do a stretch, when we do any type of movement, we're stretching both the tendon and the muscle together. If the muscle is super strong, the muscle doesn't stretch very far, the tendon stretches a long way. If the muscle is weaker and the tendon is stiffer, now the muscle has to stretch more. And so what we're looking to do is balance these two things. So what I would suggest is that in recreationally active individuals, their muscle is stronger than their tendon is stiff, so that when they take a move, now the tendon is stretching a super long way. And so that means that the likelihood of an injury is going to be in the tissue that strains the most. And so that's where we get a lot of our tendon injuries and other things. And so what we're doing is what we found, and I've got a PhD student, Danielle Steffen, who's doing a lot of work with essentially how we should be loading to fix tendon problems. Because a lot of times people get, oh, you know, even though people say, oh, Achilles tendon rupture came out of nowhere, you talk to them and they're like, yeah, for a couple of weeks now, I've
something going on.
There's something going on. It didn't feel quite right. And then I took a step and bang, it went. And that's the issue. And so what we're doing is we're addressing those early or those tendinopathic areas where I've always got pain in the front of my knee or my Achilles or in all of these things, or for a lot of throwers in their
elbow,
UCL, in their elbow, the golfers in the inside, the tennis players on the outside. And all we're doing is we're doing these 30-second isometrics where if you've got a lot of tendon-based pain, like if you're super painful in your first few steps and then it warms up and you'll get out of it, that's a good sign that it's a tendon problem, because the tendon's super stiff first thing in the morning. As you get moving a little bit more, it's going to be a little bit less stiff. And if you have those types of things where you're really, really sore for the first few minutes, or if I go out for a run, I can barely move in the first few steps, but then I eventually warm up, those are the things that are telling you that the problem is with your connective tissues, like your tendons. And that's where we come in. We use isometrics. The reason we use isometrics is that our tissues, our tendons are super dense connective tissue. And so when we get an injury to it, we get a little bit of damage to it. The load doesn't stop going through the tissue. What it does is it goes around the damaged area. It's basically like taking a big rock and throwing it into the river. It doesn't stop the river just goes around it. And that's basically what happens to the load that we're putting onto that tendon. The only time that we're going to get, and so that's what we call stress shielding, because the strong part of the tendon,
it's taking all the load,
shields the load from going through the weak part of the tendon. And so what we want to do is we want to fatigue the strong part of the tendon so that we can get load through the scarred part of the tendon. And so the way that we do that is we pull and we hold on the tendon. So we use an isometric contraction. 30 seconds causes about 80% of the relaxation that we're going to see within that tendon. Even if you go out to 2 minutes, 3 minutes, it's only going to go 10 or 20% lower in the tension through the strong part. But as that strong part starts to relax, now the weaker part has actually got more stiffness than the strong part. And so what we get is we get load going through the weaker part, and that load is going to give the cells the signal they need to reorient and to start making aligned collagen the way that we want it to be. And so we've had incredible success with this, with a lot of people who haven't been able to do their activities that they love to do. They'll do the 30-second isometrics for a couple of weeks and they'll be able to return to play. We've done it with professional athletes. We've done it with all kinds of individuals to help bring them back. And so what we're doing is we're doing 4 30-second isometric holds with 2 minutes of rest in between. And all we have to do is figure out a way that we can get load through the tissue. So if I have a tendinopathy in my elbow, I'm going to take something and I'm going to rotate it out so that there's a heavy thing over here and I'm going to hold it in that position. So I'll have tennis players hold a fry pan out with their elbow a little bit bent. And so now they're getting load through these muscles, which are the external rotators that are going to go through that area where you get tendinopathy. If you're a baseball player, a thrower, or you have golfer's elbow, you just go the opposite way. And now you're getting load through the inside. You're getting that long load hold through the inside, stress relaxation. The damaged part gets that signal to align and to synthesize collagen in a directionally oriented way, and we can repair the collagen.
Yeah, that's awesome. And based on what you talked about with collagen, would you have them do that twice a day then for those 4 rounds? Because you could up the
You
frequency
can
per day.
easily do it twice a day. So again, it depends on how much it's limiting you. So if it's something where you can't do your activities, then yeah, doing it twice a day is going to get you back faster. And it doesn't have to be like, the heaviest load you can possibly. You just have to do a load that's going to be sufficient to allow relaxation through the strong part, get load through the weaker part. The older, the denser the scar is, the greater the load you are going to need to use, because that scar is now going to take a lot longer to get that directional signal to.
Got
So
it.
if we use a heavier weight, it's easier for us to get that signal into the denser scar. So if we have a really old scar or a really old injury, we're going to use a heavier weight to get that load through them.
Yeah, that matches some stuff I've done in the past with just heavy-ish eccentrics for 10, 15, 20 seconds. And I found just anecdotal, I can't remember where I read the study from, that a lot of tendon issues literally within a couple days started like clearing up. So it was probably maybe the isometric portion of it that was
the
doing
slow
it.
Component.
Right.
So that's the Alfredson protocol. You do
Okay.
your heavy eccentrics, you do heavy concentrics. The heavy component means you go slow. That's the force velocity relationship. So when we realize that, okay, all of these things that are having a beneficial effect are just slow moves. The slowest type of contraction is an isometric contraction because there's no movement at all. So by definition, it's the slowest. And so that's why we went there. And you put that together with a bunch of other data from horses or from other things where they decrease stiffness, and they saw that the tendons went to looking beautiful again. That told us that what we're trying to do is decrease that stiffness is important, because that's how we shield the injury. So we don't get a lot of tendinopathies in kids because their tendons aren't stiff enough yet to shield that little injured area. And because they can't shield the injured area gets loaded, and so we don't see that scar formation. As we get older and older, we're going to have stiffer connective tissue. We're going to be able to shield any injury really, really well. So as I get older, again, I'm going to have to use a heavier weight because the connective tissue is going to be stiffer at the beginning. So in order for me to overcome that shielding effect, I need to have a bigger load.
And for isometrics, for people listening, one thing that goofed me up for quite a while I had to unlearn was, like, strength and conditioning wise, you're kind of classically taught an isometric is the muscle, quote unquote, not really working because it's not moving. But what happens is I'm like, well, go do a wall sit for 2 minutes and tell me your quads aren't doing anything. Exactly. And it's the muscle is still contracting, but because there's play in the soft tissue, the joint is isometric, meaning the joint space isn't changing an angle, but the muscle is still doing work because it's pulling on all that soft tissue.
Yeah, the muscle has to do a lot more work, because what we normally use our tendons for in our matrix is to have momentum in the movement and to capitalize on the momentum so that we get stored and returned energy for free. So if you want to make an exercise hard, if you think a push-up's easy, that's great. Do a 30-second down, 15-second up push-up. That's actually going to use your muscle much more, because when you're doing a normal push-up, you're storing and returning energy in all of these connective tissues throughout the system. And the result is you get a lot of bounce back where you don't have to use your muscle as a motor. If you actually want to really test your muscle, you go slow movements, because now you're no longer storing and returning energy from the series elastic component. It's all the muscular component that has to work much harder. And that's, again, as the series elastic component is doing less of the work, we're going to get better signals to potentially both the muscle and the tendon.
And I think that matches, there's an old study, I think from Australia, where you had to do a bench press with at least, I think it was a 6-second pause at your chest to try to eliminate that stress shortening cycling effect, which is a much longer pause than even people doing pause bench press would be doing. Or you can do it from the bottom as like a starting position where now you're already in that position and it's concentric only.
Yep. And that's what we see with a lot of different things that we do when we're doing supplementation or we're doing training. You're not going to see a change with a squat jump, but you're going to see a change on a counter movement jump. The counter movement jump, you're storing and returning energy. So the connective tissue stiffness is really important. On a squat jump, you're starting from a one position. You're not storing and returning energy. You're just trying to produce that rate of force development. And so we don't see as much of a performance change for a lot of the connective tissue work that we do if we're only doing a squat jump and we're not looking at something like a counter movement.
Yeah. Awesome. Well, thank you so much for all your time today. We really appreciate it. And if people are in the area and want to enroll in your study, how would they find you?
Yeah, so once everything's approved on this end from our IRB, it's going to be on clinicaltrials.gov, or they can email me at kbaar@ucdavis.edu. And that's just a way that if they're in the Davis area and they want to be part of some of our studies, we're happy to have them.
Awesome. And are you looking for any more graduate students if people are interested in that route?
So I've got a good cohort right now. I'm always interested in supporting young scientists. So if there's exceptional young scientists, I'm always interested in looking at opportunities to increase the number of the individuals that we can get in and get doing outstanding musculoskeletal work so that we can improve quality of life for as many people as possible.
Awesome. Well, thank you so much for all your time today, Dr. Barr. We really appreciate it and sharing all your wisdom. Thank you so much.
You're welcome. Thank you for having me.
Thank you. Thank you so much for listening to the podcast today. Really, really appreciate it. A huge thanks to Dr. Keith Barr for taking time out of his busy schedule to come on here to share all the different protocols and different research and everything that he's done over the years. Really, really appreciate him being so open with all the information. If you've enjoyed this and you want to learn more about how to use nutrition and recovery tactics to maximize body composition and performance in a complete flexible system, check out the Flex Diet certification. It is open now through Monday, June 13th, 2022 at midnight. So go to flexdiet.com, flexdiet.com for all the information. If you have any questions, there'll be a way you can contact me there. I'll do my best to answer any questions you have. If you're listening to this outside of that time period, then you can go to flexdiet.com also and get on the wait list for the next time that it will be open. So thank you so much for listening. Really appreciate it. If you enjoyed this podcast, please leave us a review, whatever stars you feel are appropriate. Send it to someone else. And I would appreciate any feedback you have, other guests that you would like to see, and other information. I will do my best to get other people on the podcast. Thanks again to Dr. Keith Barr. Make sure you check out flexdiet.com as it is open now. We will talk to you again in just a few days.
Hey, what are you doing? I dropped my gum. Hey, lady, would you toss my gum up? You could have taken it out of the wig first.